And when you want to find the derivative of an inverse function, you can use the derivative of the original function to help you calculate that. Maybe this theorem is a little complicated to understand, so I'll show you the proof, and maybe through that you can understand what it's saying. So let's say you have a function, f, and then its inverse, that you want to find the derivative of. There are some technicalities you want to make sure are satisfied in terms of the inverse also being differentiable. But let's ignore all that for a second, and let's just think about it that way. If you have a function, and you apply it to its inverse, by definition of inverse, the result is x. You have x, you apply f inverse, and then you apply f, you go back to the beginning, to the starting point. A function and its inverse, they kind of cancel each other out. Okay, how can I use that? If I use the chain rule, I call this thing u, and this is f of u, equals x. And the chain rule is going to tell me that if I derive both sides, d dx of both sides, so that's kind of implicit differentiation there, dy dx, du dx is what I use on the left, and then by the chain rule, right, this is the left side is using the chain rule, the right hand side is just 1 because I'm deriving x. It's a linear function with slope 1. The derivative is the slope, it's 1. So what is dy dx? Is the original derivative, the derivative of f, so f prime of u. What is du dx? That's the derivative of this, so f inverse prime of x, which is what I want to know. Now f prime of u, remember what u was, so f prime of f inverse of x times f prime, f inverse prime of x is 1. So if I reorganize things, this is what I want to know, the derivative of the inverse. I can write things as f prime of f inverse of x. Try this, I'll divide that on the other side. So take this and I'll divide on the other side to get that f inverse prime of x, so the derivative of the inverse is 1 over f prime of f inverse of x. Now if you want to go point by point, this theorem also has things better written for us. They're using the variable for the original function as x, so they want that to be a y instead. So what they want is f inverse prime of y equaling 1 over f prime of x, because that's the inverse of y, so that's x. So we're saying that f of x equals y, and therefore f inverse of y is x. So that is the general rule. And I understand this may not help you, so I'll repeat this now with a concrete example with exponents and logarithms. So what do I do if I want to find what the derivative of ln x is? You see the answer on the screen, but how do I get to it? So I'll do it that way. I'll consider e to the ln of x. I know that equals x, because ln and e to the x are inverse functions. So if I start with x, apply ln to it, and then exponentiate that, I do get x back. Remember that this only works, I'm only allowed to plug in a number into a logarithm if x is positive. That's why I have this important restriction there. So I derive both sides to reach my answer. So this is, I'll use the chain rule here on the left. The right hand side is just 1. The derivative of x is just 1, like we said. But then e to the u, which is what I'm deriving, I derive that with respect to x, dy du, du dx. So that's the chain rule. I think I may have spaced that out too much. So what's dy du? I'm deriving e to the u. That's just e to the u, the derivative of that. And du dx is the derivative of ln x, which is exactly what I want to know. So I want to know this. So what's e to the u again? U is ln x, so that's e to the ln of x, dx of ln x. So I'll treat this as though this is the variable, which is what I want to know, the unknown, and I'll divide that on the other side. But also note that e to the x, or e to the ln x rather, is just x. That's the original thing. That's the original equation we started with. So that's x times the derivative of ln x. If I divide x on the right hand side, then the derivative of ln x is 1 over x. So now we can, instead of repeating this reasoning every single time whenever you see the derivative of a logarithm, you can use this property.